Welcome to Paris class number 132, and today we're talking about cars in crosswinds. So in the last podcast, podcast 131, we looked at the setup for this, so CFD and validating this with experimental results. In this podcast, we're going to be going through the results of that CFD. And to do that, we're going to be looking at a paper called Numerical Investigation for the Influence of the Car Underbody on Aerodynamic Force and Flow Structure Evolution in Crosswinds. And this is open access, so you can find it in the link in the description. And if you're listening to this on Spotify or Google Play or whatever, you can find the video on Spotify and or YouTube. And on YouTube, you can find our other as well, some goodies for you. So let's move on here. So let's recap a few things that are important for this podcast. The first thing is that the car is traveling at 108 kilometers per hour. So this is quite fast, and this is now in the part of the velocity where the car's drag and aerodynamics in general are very important. So below about 60 to 70 kilometers per hour, a car's drag is typically seen as less important as the friction, like the rolling resistance of the car on the road. And that is generally the case. Above 60 to 70 kilometers per hour, then the drag starts to become much more important. In fact, it becomes the dominant resistive force. But also lift and side forces also become quite important. Now with this research here, they're looking at a car in a crosswinds, and they're simulating this by actually rotating the car. So they maintain the exact same velocity of 108 kilometers per hour, which is 30 meters per second. But they're just rotating the car now so that the angle that the velocity is coming in on is at a different angle. So the actual head-on velocity is less than 108 kilometers per hour because some of that velocity is coming now from the side. So what this means is that the cross-sectional area for the drag should also change as well when you think about it, because if we look at what drag is, and if you look at our video on YouTube called Automotive Aerodynamics number 9 in particular, we look at drag of a car and some of the different metrics that we use to determine the drag, including the drag area. And the drag area is very important because this not only takes into account the drag coefficient, but also the area of the car. So if we have, let's say, anything, it could just be like I'm going to say a brick for now, just like a very simple shape, a square. Let's say rectangle actually. So we have a different area here. We have a rectangle and we have the flow coming in. Now we have a certain cross-sectional area that this flow is going to see, which is going to be this much here. And if you're watching this on YouTube or Spotify, you can see what I'm drawing here. If you're listening to this, check out the video instead and you can see what I'm drawing here. Now if we have the flow coming in at an angle here, the cross-sectional area that it's going to be seeing is more like this. So now this area is obviously greater than the first one. So when we have a drag, which drag equals half times the density times the velocity squared times the area times the drag coefficient, the area is going to be changing. So what I think is that the area difference in area should also be taken into account and not just the drag coefficient, because that is like a kind of like a pseudo drag coefficient that we're looking at. We're not really looking at the drag coefficient in particular. We're looking at the changes in drag, which are then decomposed into the cross-sectional area and the drag coefficient, not just the drag coefficient. So I wanted to just go through that first so we get that groundwork out of the way first. Now, another thing that is important is that this research looked at two different models, Model A and Model B. And if you don't remember what they were, I'll just quickly recap them now. So Model A they're both exactly the same except for the underbodies. At least that's what they say. I'll go into a second there. One other thing which I noticed which was different. But first, let's cover the underbodies. So in Model A, we have a very flat underbody. It's just like the entire underbody is covered with these panels effectively, which you can get in real life. And this is becoming more and more common in automotive engineering. So if you look at like a manufacturer, an OEM, and you get a car and you look at the underbody, there's a good chance these days that the underbody will be covered. And there's a very good reason for that. The reason is because this actually reduces the drag of the car typically, and also allows the diffuser to work better. Now, in addition to this, the traditional way of making underbodies of cars was to keep them completely exposed. So you have the exhaust, you have the drivetrain, you have the spare wheel here, even the gas tank they're all exposed. And so that allows the flow to hit a lot more object, which then makes it more turbulent, makes it detach typically, and then that means that the diffuser won't work as well either. So that's the main difference between Model A and Model B, at least that's what is said. One other difference that I saw when I was going through this podcast, this data, which I'll quickly touch upon here, is the wheel housings. So in figure 7 here, you can see that the different wheels of this Model A, the wheel housings are quite small. The wheel takes up most of the housing, and that's actually very good for aerodynamics, as I'll mention in a second. But for Model B, you can see that the wheel housings are much bigger. Now, that's not as good for drag. The reason why is because the bigger the wheel housing is compared to the actual wheel, so the less of the wheel housing the wheel is taking up, the more the flow can get in there and just move around and hit more walls and increase the drag, increase the pressure drag typically. If you have a wheel house and you take this wheel and you put it in there, it takes up most of the wheel housing, there's not a lot of room for the air to come in and, like hit around and jostle around and then come out. So that typically reduces the drag by quite a bit. And generally speaking, it's like 5 counts, 10 counts. That's the general range that we're looking at here. So that's just something I wanted to cover as well. That is a difference between these two cars, because from what I could tell with this paper, that wasn't covered that well, if at all. So I just wanted to cover that there. So let's move on to the effects of crosswinds on these cars. In figure 6, we can see the effects of the yaw angle on these two different cars, Model A and Model B, on the drag coefficient, side force coefficient, and lift coefficient. So first of all, the side force and lift coefficient, the side force increased pretty much linearly with increasing yaw angle. So at a 0 yaw angle, the side force coefficient was like 0 almost. At 30-degree yaw angle, which is a very extreme yaw angle, the side force coefficient is like up at about around 1, because that's quite high. And both models are quite similar. Model B is usually a little bit higher in terms of its side force than Model A. For the lift coefficient, when we increase the yaw angle, the lift coefficient kind of increases in a kind of quadratic fashion. So at around 0, that's where we get the 0-degree yaw angle. That's where we get the lowest lift coefficient. And as we go up to 30 degrees, the lift coefficient increases quite a lot to like 1.3, which is actually phenomenal when you think about it, because that's like airfoil kind of territory to get such a high lift coefficient. So something which isn't really supposed to be producing a lot of lift, at least not by design, is actually producing as much lift as something that is designed to produce lift, which is an airfoil. But in addition to that, the drag coefficient is also quite bad. So the drag coefficient stayed relatively the same across the yaw angles, which is quite surprising, but it was around 0.3, which is not very good at all. Like, that's really bad. That means you get a lift to drag ratio of like 4, maybe 3. So that's not very good. But still, the lift coefficient is quite impressive by itself. Overall, Model B had a greater drag coefficient, and that's because you have this rough underbody and also the diffuser. So the rough underbody meant that the diffuser couldn't really work properly. It also had a greater lift coefficient and side coefficient. So that's quite interesting. We'll get into some reasons why. For example, in figure 7, we can see the pressure distribution on the cars. We have Model A on the left and Model B on the right, and this is at a yaw angle of 15 degrees. Again, at a velocity, a total velocity of 108 kilometers per hour. So figure 7 shows why the lift for Model B was greater than Model A. And that typically comes from the rear bottom, so underneath the underbody near the diffuser. If we compare the two between Model A and Model B, we see for the first part of the car, the pressure underneath was quite similar. It was around like maybe minus 200 pascals. As we get to the rear axle, that increases dramatically for the Model B as opposed to Model A. It stays about the same, minus 100, minus 200 pascals. Model B increases up to like 300 pascals almost, 250 maybe in some regions. So we have so much more pressure underneath on Model B than Model A. And because lift is just the difference between pressures on a surface, which pretty much is all forces, but lift in this particular direction is up, we get a much greater lift coefficient, and that's why we get this increased lift coefficient for Model B. For on the roof and the upper, like on the top of the car, the pressure distribution is quite similar for both models. You could argue that there's probably a little bit lower pressure around the rear left corner of the roof for Model B than Model A, but it's still minimal. Like, most of the car is very similar, so that's a little bit surprising that they are so similar, but considering that the underbodies have such a big difference in the pressure, that's why we're getting this change in pressure in this lift production. So moving on to figure 8, we can actually see a pressure coefficient distribution over the top of the car. So if you take the center line of the car, and let's say we have paint here, if you have the center line of the car and we're just going over the top, we have the pressure distribution over there. And Up until about the rear window, the pressure coefficient is very similar for both Model A and Model B. But once we get to the rear window, we start to get significant differences for Model B compared to Model A. Typically, the pressure coefficient is like a little bit ahead of Model A, if that makes sense. And to understand why, we need to look at figure 10, because this only gives us the pressure coefficient. So in figure 10, we can see, I'll zoom in a little bit here as well for you. So in figure 10, we can see the models with different yaw angles from 6 degrees to 24 degrees. And we see the streamlines around there. So we're focusing on 15 degrees first, and it shows the vorticity in the coloring and the streamlines. So figure 10 shows that there's a significant difference in the wake. So I'm looking at this part here just behind the car. Both models feature a vortex pattern, so you can see there's a vortex here and a vortex here. But Model B shows this vortex is much closer to the ground, so it's lower. This changes the flow above it, so the flow up here is now like taking up more of the rear, and hence the flow over the back will also change. And that's why we seem to get this change in the pressure. Let me zoom out a little bit. In the pressure coefficient as well. That's the main reason why we're getting this, I think. Now let's move on back to figure 9. Shows the pressure coefficient of the underbody. And this is quite interesting. This is where we can see the effects of this rough underbody on this pressure. So we can see that, again, we have lower pressure, generally speaking, over the entire underbody of Model A compared to Model B. But also in the left rear corner, just before the left rear wheelhouse, we get an increase in the pressure here. And on the leading edge, we get a reduction in pressure. What is happening here, I think, is that the flow coming over this front leading edge effectively is separating, because this is quite a sharp corner, and then it takes quite a lot of distance for it to then finally reattach, and that's what's happening here. That's when we get an increase in pressure back here. So the flow is finally reattaching here. Let's move back on to figure 10 and finish this bit off. So increasing the yaw angle seems to have the exact opposite effect on the rear vortex for Model A compared to Model B. So increasing the yaw angle for Model A, we can see that the vortex becomes less prominent. So we see that not only does the streamlines become like less and less more and more dissipated, but the vorticity, which is colored in like blue to red, is also becoming less and less strong. So the vorticity is less. On the other hand, for Model B, when you increase the yaw angle, the exact opposite thing happens. So we get an increase in the prominence of this vortex, plus also an increase in the vorticity there. So we can kind of assume, like, we can't say for sure, but we can say with pretty good confidence that the vortex is getting stronger in this case, because it is getting slightly bigger, and also the vorticity is dropping a lot. So the magnitude is getting greater. So the circulation would be getting stronger as well, I believe. So we can say that for Model A, if we have the yaw angle increasing, this vortex at the back of the car gets weaker. For Model B, it gets stronger. And also we can see that under the underbody of Model B, there's a lot more vorticity, as you'd expect, because you have all these exposed components, which are then like the flow's hitting, and then it can just shed in these vortices, and just general vorticity in general. So let's move on to figure 11 now. So figure 11 shows the difference between the Model A and Model B with yaw angle from the side. So we have a cross plane through the car, like halfway from the leading edge to the trailing edge. And so the flow comes around the car and from on the side, and we can see on the downstream side of the roof, we get a vortex forming on all cars, like on all configurations. And it seems to get stronger with increasing yaw angle. The streamlines through the underbody are not nearly as flat for Model B compared to Model A. So if we look at even at 60-degree yaw angle, we can see for Model A, the streamlines are a little bit tilted, but still quite flat. And as we go all the way to 24-degree yaw angle, they're very flat compared to Model B, where the streamlines are very angled. So what this means is that these streamlines are going to start going into other parts of the car, like in the underbody, for example, in the wheel housing or around the fuel tank or whatever. And that's going to create a lot more drag there, a lot more vorticity. And we can also see actually there's additional vortex that does form around the wheel area for Model B. So this vortex F here. Now, I mentioned streamlines here. And if you don't know what streamlines are and the differences between streamlines, streak lines, and path lines, check out our video on YouTube called Aero Fundamentals number 9, we go through that exactly, and that's a very important concept. That way you can understand what streamlines are. So we can see that the rough underbody makes quite a big difference in terms of the vorticity that's coming from the underbody of Model B compared to Model A. That's also going to change the drag and lift and side force characteristics. Now let's move on to figure 14. So this shows the Q criterion, normalized Q criterion isosurfaces at different yaw angles. So the Q criterion is a good way of telling where a vortex is. It's not foolproof, but it is like 99.9% foolproof. There are like very extreme circumstances where it breaks down, but generally speaking, it's very good. So wherever we see these white like tubes, that indicates that we have vorticity forming. Oh, sorry, vortices are there. Not just vorticity, but vortices. And figure B shows that there's a lot more vorticity and junk coming off of the Model B's underbody, as expected. And the vortices downstream of Model B seem to be much more plentiful and larger than Model A. This indicates that there's a lot more lower pressure on the back of the car because vortices are low pressure cores. If you get a vortex in a free stream flow, the free stream flow will be at a higher static pressure compared to the core of the vortex. Vortices are lower pressure. So if we have low pressure at the back of the car, what do you think that will do to the drag of the car? I'll pause it here just to think about it and then come back. Okay, so I assume that you've paused it. So if you have low pressure at the back of the car, more low pressure, that's going to increase the pressure drag of the car, increase the drag in total. Also, these vortices at the back are probably going to change the lift characteristics as well, and where the downforce and lift are being produced along the car. So in figure 15, I'll zoom out a little bit so we can see in total what it looks like. We have the streamlines going around Model A and Model B for different yaw angles through the underbody. And it's very telling, like the effects of these different underbodies on the flow. So at 0 degree yaw angle, which is straight on, even from here, the flow from the underbody of Model B is much more chaotic than Model A. You can see that the flow comes up, it jumps up a lot more, there's a lot more recirculation, and that's just a lot more messy. That will be contributing to the drag. I shouldn't say it could be, it definitely will be to some extent. But even at all non-yaw angles, the roll-up of a vortex in the wake is much more pronounced for Model B compared to Model A. So even at a 30 degree yaw angle, you can see that the vortex roll-up is a little bit bigger than in Model A, a little bit. But in other yaw angles, it's significantly stronger, like more present. So in yaw angle of 12, you can see it's barely rolling up for Model A. For Model B, it is already rolling up quite nicely. So the final thing we're going to be talking about is the turbulent kinetic energy. So this is something that that is often ignored, and it's quite an interesting concept. So the turbulent kinetic energy is how much energy the vortices have in a flow. And this is important because the more energy that is present in this turbulent kinetic energy, it generally means the more these vortices will propagate downstream, because we have to follow the energy cascade. So the energy cascade, I've talked about in a podcast probably about a year ago now. I should probably go through it again. It comes from like the von Karman idea of, not the Kolmogorov scale, not von Karman. As is that big eddies, there's a poem to it which I don't like. It's a pretty crap poem, but anyway, I'll just paraphrase it. So you have big eddies first of all, then they start to break down and they fuel these little eddies that form. Then these little eddies will break down and fuel small eddies that will form. Then these small eddies will break down and fuel even small eddies until viscosity. And then we just get viscosity and then nothing. That's the energy cascade. You have a lot of energy in the big eddies, then that flows to the next size eddies and down until we get into just viscosity, which then just turns it into heat. So if we have a lot of turbulent kinetic energy, that means we're very high up in the energy cascade, and it's going to take a lot longer for this energy to flow down to effectively viscosity. So that's what turbulent kinetic energy is. So Model B shows that there's much more turbulent kinetic energy in the wake of this car than Model A. So this means, the turbulent kinetic energy scale goes from 5 to 60. And so this means that the vortices and general wake of the car of Model B is going to propagate further downstream than Model A. So that indicates that potentially there's going to be more drag, but also if you have an object downstream, it's going to have more of a weight to deal with from Model B compared to Model A. So that's the end of this paper. Let's conclude what we've discussed. So they put cars in crosswinds. They looked at two different cars, one with a flat underbody, one with a exposed underbody. There was also a slight difference with the wheel housings that I spotted. So they found that putting cars in crosswinds greatly increases the lift and side force coefficients with increasing yaw angle, which is quite, the side force at least is quite predictable. The lift, perhaps not so much. But interestingly, increasing the yaw angle had almost no effect on the drag coefficient, which I thought was quite surprising because I thought that like cars are typically designed to reduce drag as much as possible in a certain direction. So if you were to put this car in a different direction, you'd kind of think that you'd probably get a bit of a greater drag coefficient because it's not really designed for that angle. But perhaps this car was not really designed very well to begin with, so the drag didn't change too much. It was bad all over. So anyway, the flow over the car with the exposed underbody significantly increases the lift coefficient and increases the cadence of the wake. And exposing the underbody, in this investigation at least, produced more vortices that propagated downstream more than Model A, which was the flat underbody. So those are the conclusions that we can make from this paper. And that's the end of this podcast. If you liked it, make sure to like it. And if you want to see more of this, subscribe or follow on Spotify or whatever platform you're looking or watching this on or listening to this on. And if you want to get better at CFD like this or theory, check out our courses at the link in the description. And if you want to make your experiments 2 to 4% more accurate, check out the Diameter Hawk. It's an instrument we make which accurately measures the density of air. So the reason why this is important is because the density of air changes every day. So for example, right now, actually, when I was just recording this podcast, about 15 minutes ago, it started to rain quite a lot. I don't know if you can hear that in the background. And in the morning, this is afternoon now, this is like 4 o'clock almost. In the morning, it was sunny and very different weather. So just on a regular day, the density has changed quite a lot. And even if it's just a regular sunny day, the density of air will change by 2 to 4% through differences in temperature, humidity, and barometric pressure. If you don't actually measure these changes, then you won't know what the density of air is. And that's very important because if the density of air changes a lot, it means that your results that you're getting from your experiments are not going to be accurate because your wind tunnel velocity is based on the density of air. Your forces that you measure are, the coefficients that you calculate are, everything is dependent on it. So you want to measure the density of air. And if you try to use this data to validate your CFD, then that's going to be wrong as well because your CFD is operating on a certain density of air and your experiments are not operating on that same density of air. So you want to make sure the density that you have in your experiments for your validation data is the same as your CFD. And the Atmosphere Hawk does that for you. You can measure what the density of air is and make sure it's the same for your CFD. So you can find it in the link in the description. And it's a really good instrument that's very accurate. People are very impressed with it, I would say. Like they haven't found anything which is even remotely close to its accuracy. And it's also its frequency response. So you can find it in the link in the description. And I'll see you next podcast. Peace out, amigos.